Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on November 27, 2025, about 4 days ago. It introduces adversarial flow models, a new kind of generative model that combines the strengths of adversarial training and flow matching to get stable, one-step image generation, and it pushes ImageNet 256 performance to a Fréchet inception distance of 2.38 with just a single neural network evaluation. The paper is titled Adversarial Flow Models, and as we will see later, the implications for fast, high-quality generation are quite significant. So Figure 1 gives a visual comparison of how different generators move probability mass from noise Z to data X on a one-dimensional Gaussian mixture. The top row for standard generative adversarial networks shows messy crisscrossing paths, which means the transport plan is arbitrary and unstable. The middle row for flow matching shows straight deterministic paths, but these paths distort badly when only 1 or 4 steps are allowed. The bottom row for adversarial flow models keeps those clean, deterministic paths while still allowing any number of steps, so even 1 step remains well behaved. Well, Figure 2 follows that one-dimensional toy and shows how the lambda OT weight shapes the transport paths between data X and noise Z. With lambda OT equal to 0 on the left, the paths look chaotic and generative adversarial network-like, since there is no preferred mapping. With a small but positive lambda OT in the middle, the paths straighten into a clean deterministic transport plan that still matches the data. With very large lambda OT on the right, every line becomes almost horizontal, meaning the generator collapses to an identity mapping and stops learning the data distribution. Alright, the previous figure focused on how the transport path behaves. Figure 4 instead focuses on how the network itself becomes deep. The left panel shows the multi-step setup, where a stack of transformer blocks is applied once per diffusion step between patchify and unpatchify modules. The right panel shows the extra deep single-step variant, which reuses the same transformer stack multiple times in one forward pass. This repetition creates a much deeper effective model, so high-quality images still come from a single generation step without any intermediate supervision. So Table 1 tests how the initial optimal transport weight lambda OT and the gradient penalty lambda GP affect image quality, measured by Fréchet inception distance. The left column with lambda OT equal to 0 gives very high scores around 170, which means training effectively collapses. The best region is highlighted in gray, where lambda OT is about 0.2 and lambda GP is about 0.25, giving a Fréchet inception distance near 54. This grid therefore shows that a moderate optimal transport weight is essential for stable and strong adversarial flow training. So Table 6 turns from hyperparameters to a direct, no-guidance comparison across major generative families. The table shows that classic flow matching and diffusion models reach strong Fréchet inception distances, but they require around 250 function evaluations per sample. Consistency-based methods improve somewhat, yet still stay at 1 step with noticeably worse scores. Adversarial flow rows at the bottom achieve similar or better Fréchet inception distance while using only 1 or 2 steps, which means much faster sampling for comparable image quality. Okay, while Table 6 compared unguided sampling, Table 4 focuses on single-step generation with classifier guidance on ImageNet 256. The consistency-based block at the top lists prior flow and consistency models, which reach Fréchet inception distances around 3 to 6 with 1 function evaluation. The middle GAN block improves quality but still hovers near 3. The adversarial flow block at the bottom pushes Fréchet inception distance down to about 2.4 for the extra-large model, giving the best quality at 1 step under the same latent setting. Well, Table 12 breaks down how much compute each method spends per generator update step. The first row shows flow matching needs 3 units of work, but after adjusting for many more epochs, ends up about 4.4 times slower overall. Mean flow costs 4 units, yet serves as the baseline speed. Adversarial flow needs about 14.5 units per step because of discriminator passes and gradient penalties, but the reduced training epochs still make it only about twice as expensive as mean flow for clearly better Fréchet inception distance. So the big picture is that adversarial flow models make adversarial training behave like a clean, optimal transport map, which stabilizes learning and unlocks true one-step or few-step image generation. This shift hints at future generative systems that are both ultra-fast and extremely sharp. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.